Hello everyone. Welcome to lecture 25, continuing on simple harmonic oscillation. So last time we talked a lot about the basics of describing harmonic oscillation, and particularly simple harmonic oscillators using springs. Today we're going to generalize that to a lot of very nice examples of simple harmonic oscillator. Starting with this basic idea of harmonic oscillations near an arbitrary minimum. So as a quick reminder, what we left off last time was talking about periodical oscillations. They're characterized by an amplitude, an initial phase, and an angular frequency, or equivalently a period or a frequency. And we talked about the simple harmonic oscillator that's given by a spring with a force constant k. The angular frequency is the square root of k over m, which is a big one. The equation of motion is x is equal to a cosine omega t plus phi. And everything else could be obtained from there. So the thing that I didn't emphasize all that much last time, but is very, very important, is that all of this physics comes from one piece of math. This differential equation, acceleration, d squared x 2t squared, is equal to minus omega squared times x. And that's what we're going to pick up today. So the idea is basically we can get simple harmonic oscillators simply by looking for equations that look like this. So if I give you d squared x dt squared is minus omega squared times x, you can immediately figure out that the solution is a simple harmonic oscillator, a cosine omega t plus phi. But it can be anything else. It can be a position, x, as is drawn here, or it could be some other variable. For example, if I have an angle, theta, such that angular acceleration, alpha z, is equal to minus omega squared times theta, well, the math here is the same. It's just a substitution of variables. So as long as I substitute x for theta, it's still a simple harmonic oscillator. I could do crazier things. I could do pressure or velocity or hell, acceleration. And everything would work like this. So basically, anytime I find this simple oscillator equation, the resulting physics is going to be a simple harmonic oscillator. So let's start by talking about springs again, but now a vertical spring. So instead of having our spring being placed on a horizontal table, we're going to hang a mass vertically. And what we're going to see is that the oscillations actually are completely the same. So consider the following situation. Imagine I have a hanging spring that obeys Hooke's law, meaning it's an ideal spring, and its unstretched length is L. So as you may remember, if I add a mass, it's going to stretch by some additional amount, delta L. And what's going to happen in equilibrium is that force due to the spring, K delta L, is going to cancel out gravity, and I have K delta L is equal to mg. Good so far. So this is not oscillations, this is just the new equilibrium. Now imagine that I displace the spring around that equilibrium. So I go a little bit up by a distance x. So delta L was before, now it's delta L minus x is my displacement. And if I look at my free body diagram, there are two forces. There's the force of the spring, which is K delta L minus x, and there's still gravity there. All right, so it looks a little different. It's not just Kx. So if I write this out, the total force is K delta L minus x minus m times g. And that, of course, by Newton's laws, is just mass times acceleration. But notice that K delta L was equal to mg. So this K delta L and this mg cancel each other. And lo and behold, the total force is just negative K times this additional displacement x, which is mass times acceleration. So that's exactly the same equation that I had for a horizontal spring. And therefore, the angular frequency of the oscillations does not change. In fact, all of the oscillations do not change. In fact, you can convince yourself if you do this for a spring at arbitrary angle on, let's say, an air table, so kind of an angled spring with a mass that moves like this. No matter what that angle is, you will always get angular frequency omega as root k over m, as long as there's no friction involved. Okay, so that's a vertical string. Pretty straightforward. Another example, basically a spring in disguise, is called the torsional oscillator. So there's this thing called a coil spring, which is very, very similar to a regular spring. In fact, it is just a regular spring, but instead of having that regular spring be linear, I'm going to coil it around in a little spiral like what's shown here. So when you do that and you twist that spring a little bit, what you'll find is it wants to kind of come back to normal. I twist it the other way, it wants to come back to its equilibrium position. So this is what's called a torsional spring or a coil spring. And in an ideal limit, in some sort of Hooke's law limit, the torque, the analog of the force, is simply equal to negative kappa times theta. So instead of F is equal to negative kx, you have torque is equal to negative kappa, your spring constant in quotes, times theta. And this kappa actually goes by the name torsion constant of the coil spring. But the key point is it basically looks exactly like a spring except for rotational motion. So the equations of motion are torque is equal to negative k times theta is equal to I times alpha. If I write that alpha is the second derivative of theta, and I rearrange by dividing by I, what I get is d squared theta dt squared is equal to negative kappa over I times theta, which I can rewrite as negative omega squared times theta. In other words, it's a simple harmonic oscillator. And here, if you follow through the math, what you find is that for this torsional oscillator, the angular frequency is the square root of k divided by I, kappa divided by I, where kappa is this torsion constant and I is the moment of inertia of the object that is rotating. All right, so again, this is basically a spring in disguise. Here's one simple case that's not a spring, a simple pendulum. So everyone is familiar with a pendulum. I have a heavy object at the end of, let's say, an ideal massless spring. And if I move it a little bit to the side, that pendulum simply goes back and forth, as you are well aware. Now, what you may not be as familiar with is how that equation, how that pendulum moves. So we're going to quickly derive how we can get out simple harmonic motion for a pendulum. And the pendulum I just described, where it's an ideal string with a single what's called bob, a single mass at the bottom, that's called a simple pendulum. So the idea is as follows. Imagine I have my ceiling up here, an ideal string attached to the ceiling, and my bob of mass little m is sitting down here at a length, I believe I called it capital L. All right. So first off, this is a problem we know how to solve. We've solved this problem many, many times, the same as a child on a string or a swing or many, many other similar problems. What's going to happen is this mass is going to go back and forth along a circle because the length is held fixed. All right, so there's the circle that I've drawn here. And if I want to know how that happens, I simply need to look at all the forces acting on that mass. So here I'm going to draw an angle theta, which is the angle that makes with the vertical. And I'm going to simply draw my free body diagram for that mass. So we'll start out by drawing it in this way. Gravity goes straight down and the tension goes up and to the left. Okay? Those are the only two forces acting on the object. Now I want to introduce an axis system, and the one that's going to be natural, it will turn out, is the tension axis, the ones that are parallel and perpendicular to tension. So I need to break mg, my weight, up into components. So again, this is something we've done a ton of times. Here's my weight. I'm going to break it up into, let's call it a y component that points parallel to tension, and an x component that points down here. So this small angle here is theta. The one that we care about is going to be wx. That is opposite the angle theta, so that's weight sine theta, or mg sine theta. And similarly, wy is mg cosine theta. Okay, good. So we've done this 1,000 times, hopefully pretty comfortable at this point. If I redraw my free body diagram, now along these principal axes, I have mg cosine theta here, tension, and mg sine theta, which is perpendicular. Now we're going to do something which is a little different than we usually do. We're not going to think of this as conventional linear motion. We're instead going to think of it as rotational motion, because you'll notice that that mass is simply rotating in a circle around the axis, which is right here at the point of attachment. So I can think of this as non-constant rotational motion, which we now know how to solve. And we can think of the change of this angle theta, which is indeed our angle theta in rotational motion, as simply being given by the torque equation. So if I call x and y as I've drawn them, and z is out of the plane, then I simply have that the total torque in the z direction is equal to the moment of inertia of that point mass times its angular acceleration, alpha z. So let's figure out what the torque and the moment of inertia are. So first off, I want you to take a quick second. Here's my free body diagram, and I'm telling you it's rotating around an axis which is along the direction of the tension. So the question for you is, which of these three components of the forces causes torque? The answer is mg sine theta. You'll notice that tension is pointing straight towards the axis of rotation. There's no torque. Mg cosine theta is pointing straight away from the axis of rotation. No torque. The only one that causes torque is mg sine theta. You'll notice that if theta is positive, the way I've drawn it, then the torque is favoring acceleration towards the center, decreasing theta. So if you actually do this properly, you do r cross f. Here r is this vector here that points in the point of origin to the center of that mass. So r cross f, use your right hand rule, you'll find that this is into the page, negative z direction. So putting this together, the torque is negative magnitude of the force, mg sine theta, times the radius at which it acts, which is simply the length of the rod, the length of the ideal wire, L. And that is equal to I times alpha z. Okay? This is mg sine theta L with no additional factors because mg sine theta is perpendicular to that radius. What about the moment of inertia? So this is a point mass at a distance r. That is a moment of inertia we know and love. So of a point mass, the moment of inertia is m times the radius squared, so m times L squared. And if I plug that in, I get negative mg L sine theta on my left is equal to moment of inertia I, m L squared, times alpha z. Let's go ahead and try to solve this for the angular accelerations. You'll notice the m's cancels, one of the l's cancels, and then I divide through by L. I get that alpha z is equal to negative g sine theta divided by L. Or in other words, the second derivative of theta with respect to time is equal to negative g over L sine theta. So this is actually the equation of motion of the pendulum. Now, you will notice that this is not immediately exactly equal to negative omega squared times theta. And yet we know that pendulums exhibit simple harmonic motion. So this is something that you guys should keep in mind. With pendula, it is not always the case that they exhibit simple harmonic motion. It is only the case that it is a simple harmonic oscillator if the angle theta is small. Why do I say that? Well, let's take a look at sine of theta. There are various ways to do this. I'm going to use something which hopefully you're comfortable with, which is the so-called Taylor series. So the Taylor series for sine of theta is going to expand sine of theta in terms of powers of that angle theta. So the formal definition, you may remember the Taylor series for a function f of theta around the origin is f of 0 plus theta times the first derivative of f calculated at 0 plus theta squared over 2 factorial times f double prime of 0, and so on. If you do this for sine of theta, what you may know is that the first derivative, f of 0 is 0, sine of 0 is 0. The first derivative is 1, that's cosine, so that's theta. And the next correction is theta cubed over 3 factorial, and so on. At leading order, if theta is very small, then this guy, theta, is much, much greater than theta cubed. So if theta is much less than 1, then theta is much greater than theta cubed. In other words, for small angles theta, sine theta is approximately equal to theta. So that's what we're going to actually use, this so-called small angle approximation. Let's go ahead and plug that in to our equations of motion. And what we get is d squared theta dt squared is now equal to negative g sine theta becomes approximately theta divided by L. And lo and behold, this is indeed negative omega squared times theta with the identification that omega squared is g divided by L. So that is why pendula exhibit simple harmonic oscillatory motion. And the key point that you will need to keep in mind is this only works for small angle. So here's what I've written on the slide. Omega is the square root of g over L. If I solve that for the period t, that's 2 pi times the square root of L over g, using that t is 2 pi over omega. And while it is true that this is only something that holds for small angles, it turns out it doesn't need to be too terribly small. So to give you a sense, if theta is 15 degrees, which is, what is that? Around 0.3 radians, don't quote me on that. You're still very, very close to simple harmonic motion. If you use this formula, you'll be almost exactly right with your period up to about 0.5%. So that's a part in about 200. So it's a very good approximation at small angles. Eventually, if you get up to like a 45-degree angle, this will not be true. And then it's not such an easy problem to solve. But for our class, we're mostly going to be thinking about small angle oscillations of the simple pendulum, and then this will be the angular frequency. And the equation of motion will still simply be theta of t, now instead of x of t, is equal to a cosine of omega t plus phi. So it's the exact same equation of motion, but now for the angle instead of the position. All right, so let's now get a little bit of practice on this. Imagine I hang an apple of mass 0.1 kilograms from the end of a long ideal spring with a force constant 1.5 newtons. So there are two ways that this guy can do simple harmonic motion. Option 1 is that it simply bounces up and down. So let's call that angular frequency omega 1. Option 2 is that I make it like a pendulum. So I move it a little bit to the side at a small angle, and it oscillates with some frequency, which I will call omega 2. And let's say that I tell you that omega 2 is 1/2 of omega 1. Based on the information I've given you, what is the length of the unstretched spring, which we call capital L here? All right. So I assume you've had a chance to do this problem. If not, go ahead and take a chance right now. Basically, what we're doing here is we're simply getting a little bit of practice using our formulas for simple harmonic oscillations in two different types. And then we're going to put them together and just do a little bit of algebra. It's not too bad. So as a quick reminder, I have two modes of harmonic oscillation, what I'll call the bouncing spring. That's where that apple was just bouncing up and down. So for the bouncing spring, the angular speed, omega 1, is simply going to be the square root of k over m. So exactly like we used last time, as I said, vertical spring, it's the same answer. And so we can go ahead and even plug in some numbers. We know the spring constant k is 1.5 newtons per meter. We know the mass m is 0.1 kilograms, so this turns out to be 3.873 radians per second, or just inverse seconds. All right, so that's the bouncing spring. How about that simple pendulum? So for the simple pendulum, the omega, which we've labeled omega 2 in the previous figure, is the square root of g over L. Now here you should be a little bit careful for this particular problem. L is the length of the pendulum, which I will label LSTR for stretched. This is the stretched length of that spring, which is just the unstretched length labeled capital L plus this additional stretching labeled little delta L. All right, so there's my omega 2, and what I know is that that is simply 1/2 of omega 1. So I know omega 1, I certainly know g. That means that I can go ahead and solve this guy for the stretched length with a couple of lines of algebra. And what I get is that the stretched length is 2.613 meters. Okay, so here I've used all my harmonic oscillation. Everything's pretty much good to go. There's only one thing left, is that they actually ask me to solve for the unstretched length L. So in order to do that, I simply need to solve for delta L. And in order to solve for delta L, I'm simply going to use Newton's laws. So I'm going to draw the free body diagram in equilibrium. So in equilibrium, there's the mass of the apple, there's the weight of the apple acting down, and then the spring is acting up, and that is K times delta L, the additional stretching. So in equilibrium, the total force is equal to 0, which means that K delta L is equal to m times g. You can solve this. Delta L is mg divided by k, which turns out to be 0.6533 meters. And finally, if you plug that into this equation, solve for L, the unstretched length of the spring turns out to be 1.96 meters. All right, so 60% of that was algebra, but the key things to remember here are if I operate it as a bouncing spring, the angular frequency is root k over m. If I operate it as a pendulum, that's root g over the length of that pendulum wire. All right, so that's the unrealistic pendulum. In reality, of course, we have realistic pendulums, also called physical pendulums. And the key difference here is that in a physical pendulum, the mass isn't quite all distributed at that pendulum bob. So I'll try to show this, probably fail, but let's have the fun. Go ahead and open up the camera here. All right. So if you want to do a simple pendulum, you can't do it perfectly, but a pretty good approximation is a cable. So you presumably have thousands of charging cables in your house. You have a relatively light string, a relatively heavy end, and what you find is when you let it go, it oscillates. Here's a very long length. If I decrease the length, it oscillates faster or slower. Faster, square root of g over L, so if L gets smaller, omega gets larger, it goes faster, and indeed it does. And in a non-ideal situation might be, for example, a pen. This is my fancy Apple pen. But what you'll notice with the Apple pen is that it's not the case that all of that mass is held at the end here. The mass is evenly distributed. So if I create this and make it into a little pendulum, still oscillates, not quite forever. It's friction-full, but it oscillates. Or you remember the monkey toy I played with in the last example, in the last class. Those are all examples of non-ideal pendulums or physical pendulums. And it turns out we can solve those pretty straightforwardly too. So the way we're going to do this is a nice little drawing here. I'm going to go ahead and try to redraw this on the next page. So imagine I have some complicated object, our physical pendulum. And it looks like whatever it looks like. I don't really care. It looks like this blobby thing. There is an axis about which it rotates. And somewhere in this figure is the center of mass. I'm going to go ahead and label the center of mass as being right here. Why do we care about that? Well, we care about that because gravity is the only important force acting on this object. There's a normal force holding at the axis, but the only thing that's going to cause torque on this object is gravity. And we know that gravity acts at the center of mass. mg downward is acting at the center of mass. And so if I have these two, I can do a couple of things here. I can label a vertical, I can label an angle between them, and this angle right here, theta, is describing the rotation of this object, right? Notice this looks a lot like my simple pendulum. I have my axis of rotation. The bob is now mg, acting right here. And if you think back to that free body diagram, indeed, this is basically the same thing again. So I can take that mg, which is pointing straight down, and I can break it up into components. And I apologize, I'm going to go ahead and do this by erasure because I think it's nice to have it all in the same figure here. So I'm doing the exact same thing I did on the previous example of the simple pendulum. I find that mg cosine theta points parallel to this radius vector, and mg sine theta points perpendicular to it. And the final thing I want to label on this drawing is the distance between the axis and the center of mass, d. So d is the distance between the axis and the center of mass. All right, so there we go. And what you'll notice is that this is identical to the free body diagram, and therefore to the torque diagram of the simple pendulum. The total torque in the z direction is simply this perpendicular force, mg sine theta, times the distance. Previously I called that L, now I'm calling it D to keep in line with the book. It's negative because it's generally pushing it towards the center. It's a restoring force. So mg sine of theta times d. And that is simply equal to the moment of inertia I of the object times alpha z. So again, I'm going to solve for alpha z. Alpha z, which is d squared theta dt squared, is equal to negative mgd over I times sine of theta. And this now looks identical to the regular pendulum, the simple pendulum. The only difference is instead of having m over L, I have mgd over I. Or sorry, root g over L, I have mgd over I. And so I'm going to do the same thing I did with the physical pendulum. I'm going to say, assume the angle is small. Assume small theta. Then sine of theta is approximately equal to theta, meaning d squared theta dt squared is equal to negative mgd divided by I, approximately I should say equal to mgd divided by I times theta. Sine theta is approximately theta, which is our equation for a simple harmonic oscillator. And so we see the angular frequency omega is the square root of mgd divided by I, where m is the mass of the object, g is g, d is the distance between the pivot point and the center of mass, and I is the moment of inertia about the axis of rotation. So that is the physical pendulum, or the realistic pendulum. And in the end, it's really the same bit of physics as the simple pendulum. There are just a few more things that you have to deal with here, because you have to know the moment of inertia as well as this distance d. All right, good. So let's get a little bit of practice on that. Imagine I have a 1.8 kilogram monkey wrench pivoted 0.25 from its center of mass, 2 meters from its center of mass, and that it swings like a physical pendulum. The period for small angle oscillations, meaning small theta, is 0.940 seconds. So figure out what's the moment of inertia, and if I started off at 0.4 radians from its equilibrium, what's the angular speed of the wrench as it passes through equilibrium? Very good. All right. So this is a stereotypical example of a physical pendulum. I think it even says physical pendulum in the problem statement. Yes, indeed it does. So we simply have to pick out the relevant quantities. What I was told to me. The mass is 1.8 kilograms. Good. It's pivoted 0.25 meters from its center. That means that if here's my monkey wrench, here is my incredibly bad attempt to draw a monkey wrench. Every year it gets worse. Does that look like a monkey? It looks like Pac-Man. Well, don't hire me to do your car mechanic stuff, and then you'll be fine. So here's my artist impression of a monkey wrench. And what's told to us is that the distance between the axis of rotation and the center of mass is 0.25 meters. That's this thing we labeled D, 0.25 meters. And we know that the period for small angle oscillations T is equal to 0.940 seconds. All right, so rule number 1 of harmonic oscillation that I taught you is if you're ever given anything that's not omega, go ahead and convert that to omega. Omega is much easier to work with, so we'll go ahead and do that. Omega, your angular frequency, is 2 pi divided by t. Hopefully I did this in my notes. Let's see. I did indeed. That turns out to be 6.684 radians per second, or inverse seconds. So now I'm cooking with gas. I can go ahead and plug that in to my formula for the physical pendulum, which is a reminder is omega is root mgd divided by I. And what does this part of the problem ask for? It asks for I. So we're almost ready to go. We know everything else in this problem. We just need to solve for I. So let's go ahead and do that. I have omega squared is equal to mgd divided by I. Multiply both sides by I, divide both sides by omega squared. I get I is mgd divided by omega squared. And then I just have to plug in some numbers. It turns out to be 9.87 times 10 to the minus 2, or 0.0987 kilogram meters squared, the weird units of angular moment of inertia. All right, so now part B. Part B says I take this monkey wrench and I start it out at an angle. Let's see if I can draw it better this time. I'll be embarrassed if you guys think I don't know what a monkey wrench looks like. I actually don't know what the monkey in monkey wrench means, but let's assume that I can at least draw something that vaguely looks like a wrench. So here we go. Here's my slightly better artist impression of a wrench that looks kind of more like a dead Pac-Man. And the initial angle, theta 0, is given to us, 0.4 radians. So the question is, if I start out at rest here, what is the angular velocity when it goes through equilibrium? So kind of when it goes through here. Okie dokie. So first off, there are a couple of different ways I could attempt to solve this problem. The big one, which will be true regardless, is that something is conserved. So I want to quickly have you ask yourself, what is conserved in this problem? Hopefully the answer you got is energy. Okay, so a big thing you should always remember with all harmonic oscillations we're going to talk about today, energy is conserved. And so if you remember back to last time, we talked a little bit about how we might do this sort of problem with energy conservation for a simple harmonic oscillator. So for a simple harmonic oscillator, I know that my equation of motion is theta is equal to amplitude, which in this case is given to us as theta 0, times cosine omega t plus phi, but since it starts out at its maximum, this would be theta 0 cosine omega t. And I could go through the equations. I could solve for the angular frequency by taking a derivative. I would find that this is negative theta 0 times omega sine omega t. And plug it in and go from there. So for example, this is, I should say, omega z. Here I want to be very careful. I'll add the subscript z to make sure that it's very clearly different from the angular frequency, omega. So omega here is the angular frequency. That's how fast the oscillations go. And omega z here is how fast the wrench is moving. Confusing, I know. But by definition, what I mean by that is d theta dt. Sorry about that. D theta dt. Okay? So I know it's notationally confusing, but omega z, I will always try to write that z to make sure it's clear on the angular velocity. And then omega without a subscript is the angular frequency. It's telling me about my simple harmonic motion. So if it were to ask you like this, I would figure out that when I go through equilibrium, that's when the sine is equal to 1, or the cosine is equal to 0. And I would say that my omega z max is theta 0 times omega. And you can plug in some numbers. I don't remember if I did this in the notes. I did not. But you'll get something of order. Let's see, what do I have? 0.4 times 6.6 something. You'll get something like, what is that? 2.66-ish radians per second. So that's close, but it's not quite right. So one thing I do want to emphasize here is this would work for a simple harmonic oscillation. In other words, this works if theta, here theta 0, which is our largest angle, is small. And theta is 0.4. So 0.4 is not huge, but it's not that small either. So the ideal way to solve this problem is actually not the way that I just said, but to just use regular old energy conservation. So if we think a little bit about regular old energy conservation is going to tell us, we can just do the initial state. So let's say the initial state, my wrench is here. And okay, from now on, my wrench will be drawn as such. And the center of mass is right there. Let's go ahead and call the initial value of the center of mass y equals 0. That means my initial gravitational potential energy is 0, and my initial kinetic energy is, of course, 0, because nothing is moving. At the end of the day, when it passes through that new equilibrium, my axis doesn't move, but now that center of mass has moved down. All right, so my initial center of mass was at y equals 0. My new center of mass has moved down to some negative value. So for this, you have to do a teeny bit of trig. The trig I can do is that I know that this distance right here is d. And I know that this angle here is theta. So if I redraw that triangle, I have d, theta, and that means this vertical distance right here is d cosine theta. Theta 0, I should say. That's the initial angle. And that means the amount of leftover distance, since I know that this whole distance here is also d, this little leftover is d minus d cosine theta, 0. Or in other words, y final is negative that because it's down by this amount. So that's d times cosine theta 0 minus 1. And now we can just go ahead and plug this in. So the final gravitational potential energy is mgy final, or mgd times cosine of theta 0 minus 1. My final kinetic energy, well, this is rotational motion, so that's 1/2 I omega z squared. Again, make sure you label that z. That's the angular velocity squared. And energy is conserved. So energy conserved means that UG final plus kinetic final is UG initial plus kinetic initial. But I chose the nice convention that my initial energy was just 0. So that means that UG plus kinetic final is just 0. You plug that in. That says that mgd times cosine of theta 0 minus 1 plus kinetic 1/2 I omega z final squared is equal to 0. Solve this guy for omega final. It is omega z final is equal to the square root of 2 mgd times 1 minus cosine theta 0 over 2 over I. And when you plug that in, oh my gosh, you get 2.66 radians per second. So that's the actual answer. I guess I guessed a little wrong earlier, or maybe it's really just so close that it doesn't matter. Let's call this 2.64 as my initial guess. So you're off by a little bit because it's a large angle. You could try this again with something like a 90-degree angle. Theta 0 is equal to pi over 2, and then you'll see that you're way off. So if I don't say the word small angle, you want to be a little careful and not use a small angle approximation. But most of the time we will keep to a small angle approximation. That'll be pretty safe. All right. So that is the physical pendulum. Big thing to remember there again is energy is conserved, just like every other example of harmonic oscillation we're going to talk about today. So we're going to do one more example of a physical pendulum. A pearl earring of mass m and radius r hangs from a woman's ear and swings as she walks. It's going to pivot at a point right around the top. And what I'll tell you is for a solid sphere, you may not remember this formula, the moment of inertia is 2/5 mr squared, where m is the mass and r is the radius. So what I want you to think about is what is the time period of small oscillations, symbolically. If m increases by a factor of 2 without changing the radius, what happens to the period? And which swings faster? The pearl earring or a simple pendulum where all of the mass is just down here at the bottom of the earring. So I want you to try to guess the answer to C first. Think about it. Which swings faster, the pearl or the pendulum? And we're going to go ahead and solve that. All right, so take a couple minutes, give this a shot. Hopefully you've had a chance to do so. So let's go ahead and go over this answer together. So I have the following situation. I have a physical pendulum that is pivoted right about its top here. The center of mass, I should say, is right in the middle. And that means that the distance between the pivot point and the center of mass is just the radius of this sphere. So that's going to make our lives quite a bit easier. First part, what is the angular frequency? So we always solve angular frequency first. Oops, I should say something. I said something a little bit wrong here. The moment of inertia is not 2/5 mr squared. I apologize about that. The moment of inertia about the center of mass is 2/5 mr squared. So as a quick reminder, since it is, of course, exam 3 eligible, I want you to quickly figure out what is the moment of inertia about this actual axis A, about the top of the earring. Okay, so This is one of the examples where you're going to want to use that parallel axis theorem. The moment of inertia about a parallel axis A is the moment of inertia about the center of mass plus the mass times the distance between them squared. And remember, d is equal to r. So that's 2/5 mr squared plus 1 mr squared. Or in other words, the moment of inertia is 7/5 mr squared. That's the one we want to use in our formula because that's the moment of inertia about the axis of rotation. So for instance, omega is equal to the square root of mgd divided by I. Here this is IA. That's the square root of mgr, d is equal to r, over 7/5 mr squared. And there's some nice cancellations. One of these r's cancels, the mass cancels, and I get the square root of 5g divided by 7r. Not particularly intuitive, but indeed it is correct. And if I want to get the time, which is what the problem asks for, that's just 2 pi over omega. Or in other words, it's 2 pi times the square root of 7r divided by 5g. So that's part A, the period of the sphere. So now let's figure out what happens when I change the mass. So as a quick reminder, with the simple pendulum, we had the following formula. We had the period, I'll label it T simp for simple, is the square root of g divided by L. And the important thing to remember is that this does not depend on the mass of the object, the mass of the pendulum bob. I can double it, triple it, quadruple it. The simple pendulum does not change its frequency. Now, if you look back to our physical pendulum, it looks like this might depend on the mass, right? Because m shows up in this formula. However, notice that the mass changes both the mass itself and the moment of inertia, I. And when we solved for the period here, what we found is that indeed the period, this is omega, I should say this is omega of the simple pendulum, is root g over L. Anyway, so if we come back to the physical pendulum, the period actually didn't depend on mass, and similarly the angular frequency did not depend on mass. And that came because the masses from m and I canceled each other. So if I double my mass, coming back to the physical pendulum, nothing changes. Omega is still the square root of 5g divided by 7r. So it's unchanged, exactly as what you would expect. Now, part C. Which is faster, the simple pendulum or the physical pendulum? So hopefully you've taken a minute to guess this, to try to use some intuition. The answer is that the physical pendulum will be faster. Let's first see this mathematically. So in the case that's asked about, we have a simple pendulum like so, a physical pendulum like so, versus a simple pendulum that kind of looks like this, thin string, and then all of that weight is at the bottom. And what you'll notice, well, actually, let's just go ahead and plug in first. The length here would be 2 times r. So if I plug that into my formula for omega simple, my omega for the simple is simply going to be the square root of g divided by 2r, or 1/2 g over r. Now 5/7 is greater than 1/2. So omega of the physical pendulum is bigger. And the reason for this is actually pretty straightforward. If you think about the physical pendulum, more of the weight is at smaller distance. If I think about kind of averaging the distance, it looks a little bit like a simple pendulum, but that weight is going to be a little bit higher than the pendulum bob. And we know that if L goes down, omega goes up, so that's why the physical pendulum goes a little faster. Anyways, you don't need to know that. It's just something you can do from the formula, but it's a little nice piece of intuition here. All right, so we've talked about torsional oscillators, we've talked about springs that are going vertically, physical pendulums, simple pendulums. There's one more piece of physics that we want to talk about today. So this is really at the edge of the calculus that we'll learn in this class, but it's sufficiently important and cool that I am going to teach it. So what we argued earlier is that oscillations will occur for any local minimum. We saw that for the physical pendulum, we saw that for the simple pendulum, and actually we saw that for some very unusual things. So you may remember we had this example last time. I have a ball sitting in an arbitrary potential here, so I have my little bowl right here, my circular bowl. It's going to go towards its equilibrium. If I move it a little to the side, it does simple harmonic motion. Move it to the side just a little, it does simple harmonic motion. So that is going to be a very, very important and very, very general property of these systems. And the reason for that comes down to the calculus of this equation. So let's go back to our spring. Here, imagine I have a perfect spring whose potential energy is 1/2 kx squared. And we're always talking about oscillations near the minimum, so near this point down here at the bottom. And what we did is we said the force is equal to negative k times x, F is equal to ma. That gave us the equation of motion, ma is equal to negative k times x. And the question is, what really mattered in order to get this equation of motion? For example, did the overall potential energy offset matter? Let's say I told you that instead I'm going to define the potential energy of the spring as 1/2 kx squared plus 10,000 joules. Well, the answer is no. That's very straightforward. Potential energy is only defined up to a constant, so this last constant just does not matter at all for any physics, including simple harmonic oscillators. Second question, did it matter what happened far from the equilibrium point? So that's a little more complicated. For example, if I were to map the potential energy of the pendulum, it would look a little something like a circle, because that's the motion that the pendulum does. You can convince yourself of this, but this turns out to be true. So x is the position of that pendulum, and y is the potential energy, which is actually also equal to y. Or proportional to y, I should say. So again, if I dropped it from way up here at the top, that's really not going to be a simple harmonic oscillator. As I mentioned, that physical pendulum is not going to be a simple harmonic oscillator. But down here, near the minimum, I said it behaved as a simple harmonic oscillator. If I want to go even a little more crazy, let's imagine I have an exact perfect spring potential, but then do crazy things off in the tails. As long as I'm staying close to the minimum, those tails don't matter at all. I never see them. So the behavior far from the minimum does not matter. And now we need to start thinking about calculus, because when I have a function and I want to approximate its behavior near a minimum, the way to do that is through this Taylor series. It's through calculus. So we don't care about the value there. If I do a Taylor series of u about the minimum, I don't care about the value. Do I care about the first derivative? Well, the answer is no, because anytime I'm at a minimum, the first derivative is equal to 0. What about that second derivative? The next order term in the Taylor series. So that turns out to be yes. In fact, if you consider our exact perfect spring, what you'll see is that u of x is 0 plus 0 plus 1/2 u double prime x squared, where u double prime is the spring constant k. It's 1/2 kx squared. And so it turns out the only thing that matters for simple harmonic oscillations is what is the curvature of the potential energy near the minimum where we are trapped. The second derivative, or the curvature, is equal to the effective spring constant k. And that's the really cool piece of physics that we're now going to exploit. near any single minimum, I can approximate, well, any single quadratic minimum. I could technically lose my quadratic term and then I'd be wrong. But near almost any minimum you would find in nature, my potential energy may be approximated by some overall offset, which I don't care about, plus a slope, which is 0, plus 1/2 times an effective spring constant times the deviation from the minimum, a parabola. And that effective spring constant is simply the second derivative of the potential energy evaluated at that minimum. So for any arbitrary potential energy surface, for example, going back to my ball in a, Going back to my ball in a weirdly shaped potential, all I need to do is figure out the potential energy as a function of position, x, take a second derivative around that point, and I will get an effective spring constant k equal to the second derivative. So that's the key to general small oscillations. Omega is the square root of this effective spring constant divided by m, which is simply the second derivative of u with respect to x squared. So something that I did in the notes, for those of you who are interested, I don't think I'm going to do it now in the interest of time. We can actually quickly rederive both the simple pendulum and the physical pendulum using this equation. It's actually pretty straightforward. You simply write now the second derivative with respect to theta divided by I, because it's angular motion. But you simply write out a potential energy, which is all gravitational, as a function of theta. That's this 1 minus cosine. And you take a second derivative of 1 minus cosine. What do you find? Well, you find negative cosine. So negative cosine is 1. You plug in all the numbers, you find out that in fact it exactly gives you the same bit of physics as we would have gotten from just doing it the other way. So I believe that's in the notes. If not, yeah, it's in the notes. I did it one way in the notes. You can do it a slightly different way. It doesn't really matter. But for now, we're going to just go on to a fun example. And I think this will be the end of the mandatory material for today. Well, there's going to be a little bit more, but it won't be too many more examples. So example 4 here is something that is near and dear to my heart. It's an example of a very nice material that I think a lot of you are going to be hearing about if you haven't heard already. So you've probably all heard of graphite. Graphite is, well, it's pencil lead actually. It's not really lead in pencils anymore. It's graphite. So it's a pure form of carbon. It's a cheap form of carbon. A much nicer form of carbon is called diamond. But if you want to get your carbon on the cheap, you're going to get it in the form of graphite. And the important thing about graphite, from my perspective, is that it's very, very tightly bound in two-dimensional layers. So if you ever actually kind of cut open a piece of graphite, image it on an atomic scale, what happens is two-dimensional layers are very, very tightly held together. They form what's called a honeycomb lattice. So the carbons sit on the edge of this thing called a honeycomb lattice. See if I can draw it. So it's kind of a top view. This is what the carbons look like. But from a side view, I have one layer, one honeycomb layer of carbons, and then another layer, and then another layer. And these are what are called layered materials, of which there are many very important ones that we're learning more and more about every day. But each of these layers is actually very weakly coupled to the layer above. The interlayer coupling are covalent bonds, the very, very strong bonds that you've certainly learned about in chemistry. The interlayer bonds are much, much weaker. They're what are called van der Waals bonds. And it turns out you can express these in terms of a force, in terms of a potential energy, which turns out to be U is equal to U0, R0 over x to the 12 minus 2 R0 over x to the 6th. Where for graphene, the approximate numbers are U0 is 6.83 times 10 to the minus 21 joules, and R0 is 3.35 times 10 to the minus 10 meters. So the question is, as I try to move one of these layers around, by a distance x in this potential energy, what's the equilibrium spacing of this material, and what is the frequency of small oscillations for a carbon atom? So mass of the carbon atom, you can look it up on the periodic table since you guys are all on the internet. I want you to take a quick second, see if you can figure out what's the equilibrium value of x and the frequency of small oscillations of that carbon atom. Good. So hopefully you've had a chance to do this. This is a nice example, and actually your homework will also be a nice example of these general harmonic oscillations. So let's go ahead and see how this works in terms of these lovely energy diagrams that I like to keep coming back to. Sorry, it's just going to be a second here. All right. So what I've told you is that the carbons, these carbon layers, live in effective potential energy, U, which is U0, some overall constant, times x over R0 to the 12th power, minus 2x over R0 to the 6th power. It's a really impressive piece of physics that they were actually able to determine this, and involves some really nice quantum mechanics and polarization kind of stuff you'll learn in the next class, 23-26, but quite a bit of quantum mechanics bootstrapped on top. But let's forget about where it comes from. Let's talk about what we can do with it. What we can do with it is we can obtain simple harmonic oscillations. So U0 with some positive constant, R0 with some positive constant. If we plot this out, x to the 12th is a rapidly increasing function. Oh, I'm sorry about that. That's minus 12th. This is minus 6. So let's try that again. X to the minus self is a rapidly increasing function near x equals 0, but then quickly decays. X to the minus 6 actually also has that property, but it's much, much less large near the origin, and then it's negative, and it decays to 0 as such because of this negative sign. When I add those two guys together, and you can just plot this on your handy-dandy graphing calculator, what you will find is the potential energy looks a little something like this. Potential energy is a function of distance, starts off at infinity, goes down below 0, and then comes back up gradually asymptotes towards 0 at x equals infinity. We'll see there is a so-called equilibrium position. And what's going to happen at the equilibrium position? What can you tell me about the potential energy? Well, the equilibrium position, as we've discussed many times, will happen at either a minimum or a maximum of the potential energy. Here it's a minimum, so it's a stable equilibrium. And if I try to move away from that minimum, first off, you'll notice I can't ever get them infinitely close together because that would cost an infinite amount of energy. I can push them infinitely far away. That's what's called the ionization or the work function. It's actually not for the carbon atom, so it's the energy to pull apart these layers. If this were electrons, that would be the ionization energy. Anyways, that's what's happening off at infinity, but we care about this as x equilibrium, this thing that's happening at the minimum of u. So there we need to do a little bit of calculus. Where is the minimum u? It's where the derivative is equal to 0. So we need to take a derivative. The derivative of this function is not too bad. It's just a polynomial, so that's u0. That still factorizes times x to the minus 12. Well, that's minus 12 x to the minus 13th. R0 to the positive 12. Minus 2 times the derivative of x to the minus 6 is negative 6, x to the minus 7th, R0 to the positive 6th. And now we want to solve for when this is equal to 0. So first off, there's a very nice property, and in fact that's what that factor of 2 was doing there. These are now both 12s. So I can go ahead and factorize that. This is now 12. U0, there's an overall factor of x to the negative 7th that factorizes. Let's do the actual x to the negative 13th that factorizes. And I'm going to also factorize an r to the 12th, r0 to the 12th. So once I've done that, then I have negative 12. I factorized out the 12, so that's just negative 1. X to the minus 13th, that's gone. R to the 12th, that's gone, so that's just negative 1. Plus 1, x to the minus 7th. I factor out x to the minus 13th, so that's x to the positive 6. And this r0 to the 6th, once I factorize, is r0 to the minus 6th. So that whole thing is equal to 0. And the only way I can make that work is if this thing in brackets is 0. So 0 is equal to negative 1 plus x to the 6th over r0 to the 6th. And that works when x over r0 is equal to 1. In other words, this r0 is indeed my x equilibrium value. That's the radius at which these guys want to sit. So as a reminder, the numbers for carbon were, what did I say? 3.35 times 10 to the minus 10. That's the interlayer spacing of graphite, of carbons within graphite. And if you actually run some numbers, if you look within the bonds, within that honeycomb lattice, that lattice spacing is going to be much less. So this is about 3.5 angstroms, 10 to the minus 10 meters in an angstrom. Between them, it's of order an angstrom. I think it's a little less, maybe around 0.8 angstroms if I had to guess, but it's a factor of 3 or 4 less. And that's saying that this is a very strong bond, so it's a very short bond. These are very loose bonds, and therefore they're very long and very easy to pull apart. So there we go. We have the equilibrium position of this carbon atom within the van der Waals potential. And the very, very important second question is, what is the angular frequency of small oscillations? So here we're going to have to use this very nice formula that for any object in a potential energy around a small angle, at small oscillations around a minimum, the omega is the square root of an effective spring constant divided by m, where the effective spring constant is simply the second derivative of u evaluated at the equilibrium position. So in order to do this, we're going to have to take that second derivative, but that's, again, not so bad. The second derivative of u is, well, let's go ahead and go through this. I had an overall factor of u 0. Still factorizes, no problem. Now, I have minus 12x to the minus 13th. So that's minus 12 times minus 13th times x to the minus 14th. r0 to the 12th, plus 12 times x to the minus 7th, so that becomes minus 7, x to the minus 8, r0 to the 6th. This is not particularly pretty, but all we have to do is calculate this at this equilibrium position. So I take the second derivative, I substitute x equilibrium, which is r0, and yada, yada, yada. You can go ahead and plug this in. It turns out the answer is u0 over r0 squared. That's what's required for the appropriate energy units. Times 156 minus 84. Very intuitive, I know. And that turns out to be 4.382 newtons per meter. So not a crazy spring constant at all. That said, m is a teeny value. The mass of a carbon is 12 atomic mass units. There are 12 nuclei in there, nucleons I should say. There are 12 protons and neutrons. In usual stable form, it can technically change. So that's 1.66 times 10 to the minus 27 kilograms per AMU. That turns out to be some very small number of kilograms. And now, if I plug in omega is the square root of K effective divided by m, this turns out to be 1.483 times 10 to the 13th inverse seconds. Something that will be useful in just a quick second is to calculate the frequency. Frequency is omega over 2 pi. that turns out to be 2.36 times 10 to the 12th hertz, or 2.36 terahertz. And now why do I care about that? So this turns out to be a really interesting fact about nature. This is roughly correct. The small oscillations of those layers are around 2.73 terahertz. They're actually a little higher than that. They're at it's a couple 10 terahertz, but I don't know the number exactly offhand. So it turns out this is something that by accident, by a very magical accident, was very, very valuable to modern physics. So the reason we now care about this material, and actually some related material called transition metal dichalcogenides, is that they are the first known examples in a massively increasing field of two-dimensional materials. So if I have that layered material of graphite, I have all of these two-dimensional layers of graphite, it turns out what I can do is I can peel off one of them. And it's amazing how this works. You go onto that piece of graphite, you take a piece of Scotch tape, put it on top, pull it off, and then just deposit that piece of Scotch tape on some other substrate, something like silicon dioxide. Pull off that, and every once in a while, very, very rarely, but not infinitely rarely, what it's going to do is it's going to leave behind a single layer, a single atomic layer of graphite or of carbon, and that's known as graphene. So this was discovered, about 2010, I think, 2008, a handful of years ago, using exactly this little Scotch tape method. And believe it or not, when you do that and you actually study this small flake of graphene, it has amazing properties. For example, it has what are called Dirac cones, and these Dirac cones make the electrons of the material behave like they're moving at the speed of light. They basically behave like photons, like particles of light traveling in vacuum. They behave completely differently than all the other materials that you've ever experienced. And it turns out that that's really cool. It turns out that's very useful for designing electronic devices. It turns out you can do a crazy number of things with that. And a couple of years after this was discovered, it's one of the quickest turnaround times between doing something, peeling up a piece of pencil lead with Scotch tape, and getting a Nobel Prize. So this was a Nobel Prize in, I think, 2013. Could be wrong about that. So the really cool thing is that they could actually identify this. The way this was found is they were actually able to see graphene in a microscope. And it turns out the only reason they were able to do that is when the light comes in, hits the graphene, it just so happens that on silicon dioxide with graphene in single layer, the oscillations between the graphene and that silicon dioxide substrate, these small oscillations, exactly what we just calculated, turn out to be very, very close to visible light, what they were seeing in their microscope. So it turns out that you can actually do this on appropriate thickness silicon dioxide substrates. You will see single layer graphene. It's actually visible in a regular microscope. That's an accident of nature, but it's an accident that got someone the Nobel Prize. The physics behind that turns out to be exactly these small frequency, these small angle oscillations. So your homework is going to be to solve for another Nobel Prize known as the Higgs boson. I think in the interest of time and in the interest of the fact that we're all remote and online, so I don't need to go blather on for another bit longer, this is all the material that I'm going to cover that will be on the exam. For those who are interested, I'm going to talk about one other thing that's not going to be on the exam, but it is a little bit at least in the book, which is what are called damped oscillations and damped driven oscillations. So the idea of this is that in reality, so I should say just quickly for those of you who aren't interested in continuing, this is all the material that will be covered on the homework and the exams. Thank you for attending, and I will see you guys all on Tuesday. For my diehards, I want to say a little bit about damped oscillations, because in the real world, there is always non-conservative forces that will cause the oscillations to decay. And when this happens in an oscillatory environment, the decrease in amplitude, these oscillations that instead of going on forever start to decrease, that is what's called damping. And the whole system is called a damped harmonic oscillator. So this is something that happens all the time, and it's something that's very useful to be able to solve. So you can't actually solve the simplest model that you might predict, which is just, oops, this guy doesn't like me right now. So you might just think, well, I'm just going to solve this by putting in friction, mu k times n. And that turns out to be a pain in the butt. It's not very easy to solve. It doesn't behave any way that you might like. That said, there is a simple model that's going to be relevant to a number of systems. It's relevant to fluid mechanics. It's relevant, as we'll see in the next class, actually to RC circuits. If you have, AC circuits. If you have alternating current, once we start talking about circuits in 2326, that turns out also to be a damped harmonic oscillator. So the simple model of a damped oscillator that we can solve is Ma is equal to K times X with a damping that is not constant, but is instead proportional to the velocity. So if I have a force that is proportional to velocity, that turns out to be a nice damped harmonic oscillator. And you may remember back when we were talking about air resistance, this is actually something that can happen. It's not drag resistance. It's what's called, I believe it's Stokes resistance, but you won't want to quote me on that. Anyways, it's air resistance that happens at relatively low velocity. You have linear in velocity behavior. So here, B is what's called the damping coefficient. You can think of that as like the drag coefficient. So big B, strong damping. 0B is what we've already solved. That's the case of no damping. And the solution turns out to have the following relatively nice form. X is equal to A e to the minus bt over m cosine of omega prime t plus phi. So here's something where I actually want to show you a little bit of the math behind this. Since we are kind of in the overtime period, I'm going to go ahead and show you where this comes from. And in the process, I'm going to show you a very nice piece of calculus which you may not have seen, namely calculus of exponential functions, imaginary complex exponential functions. So this is the damped harmonic oscillator. 1 second here. The damped harmonic oscillator. And what we said is that the equation of motion for the damped harmonic oscillator is mass times acceleration is equal to negative k times x minus damping b times v. And if I want to solve this equation, this is actually a pretty standard equation that you'd want to solve in a differential equations class. So I'm going to go ahead and bring everything over to the left-hand side of the equation and write it in the language of derivatives. So mass times the second derivative of x plus b times the first derivative of x plus k times just x is equal to 0. So this is what's known as a homogeneous differential equation, meaning that if I were able to tell you a single solution and a second solution x2, then any sum of them is equal as a solution as well. And you can also notice that if I were to rescale the solution, if I were to just multiply x by a factor of 2, nothing would change. So any solutions I can come up with, I can add them together to get the general solution. And so I want you to think for a quick second. If I want to go ahead and cancel out the first derivative, second derivative, and x itself, what's a function that looks a lot like its various derivatives? So the first thing to say is we can't just use cosines and sines. Let's say, for example, that I would guess x is equal to cosine of omega t. The problem is that first derivative, x dot, that's the first derivative with respect to time, is now like a sine, right? So it's negative omega sine omega t. And that's never going to cancel with anything. You can try to do this. You can try to imagine that I have ax, a cosine plus b sine, but I can always rewrite it as cosine omega t plus some phase. And then again, I'm never going to be able to cancel out this damping term. So that is not a good solution. What function do we know that's equal to its own derivative? Well, we do know that one. The exponential function is equal to its own derivative. Derivative of e to the t is equal to e to the t. And so we're going to propose a solution to this problem. We're going to propose that the answer is e to the t times some constant. And the constant we're going to pick, I want to make sure I'm using the same notation that we use in this. Yes, let's call it. Well, here's what I'm going to do. I'm going to do something that seems a little crazy. I'm going to propose that x has the following form. E to the I omega prime t. Actually, let's do I omega t. Where here I is the imaginary number, meaning that I is the square root of -1, or I squared is equal to -1. Now you may remember that there are some very nice properties of this exponential function when I have an I in there. So e to the I omega t is this cis thing you may have heard about. Maybe that means new things in the modern era, but back when I was learning, we learned that that e to the I theta is cosine of theta plus I sine theta. That means e to the I omega t is cosine omega t plus I sine omega t. And it turns out to be a much nicer way of writing cosines and sines because derivatives are nicer. So for example, if x is e to the I omega t, then dx dt is simply equal to I omega e to the I omega t. By the product rule, I take the derivative of the thing inside and I multiply it by the derivative of this exponential, but that's its own derivative. The second derivative is just I omega squared times e to the I omega t. And notice now every single term has an e to the I omega t in it. So when I go and I plug that back into the original equation, I have mass times acceleration, so mass times I squared, which is -1, omega squared, e to the I omega t, plus b, damping, times the first derivative, I omega e to the I omega t, plus k times the nothingth derivative, so that's just e to the I omega t, is equal to 0. And now, because every single term has e to the I omega t, I can simply cancel them. And now I see that this is going to be a correct solution. I simply have to solve for what omega is going to make this work. So I have I squared is -1, negative m omega squared, plus I b omega, plus k is equal to 0. And this is simply a quadratic equation, so I can solve for it. Omega is equal to negative b, so negative ib, plus or minus the square root of that guy squared. So that's negative b squared, because I squared is -1, minus 4ac, so minus 4 times negative m times k, all over 2a, so negative 2m. And these are the solutions to the problem. Now let's talk quickly about under what conditions this will give damped harmonic motion. Let's consider, for example, the limit where b is very small. In particular, b squared is much less than 4mk. Actually, all I need to do is less than 4mk. So under those conditions, omega is equal to negative ib plus or minus the square root of 4mk minus b squared over negative 2m. But this guy right here is the square root of a positive number, so it's just a regular old positive number, meaning that omega can be written as two factors. negative IB over negative 2m, so positive IB over 2m, plus or minus the square root of some positive number, 4mk minus b squared, over 2m. And when I now plug that in, so these are the two solutions, that means that my regular full solution for x is a times the first solution, e to the I omega 1, so IB over 2m, plus root 4mk minus b squared over 2m, t, plus b times e to the I times the opposite. And now, in the interest of connecting it to the notes, I'll leave the b over 2m alone because that's the same thing that's written in the notes. But I'm going to call this thing right here omega prime. So I have that plus omega prime times t. Or sorry, minus omega prime times t. So now I'm taking the minus square root. So these guys you can double check are individually solutions to the equation. And that means I can add them up and I can get the general solution to the equation. So I can factor out this e to the I times b over m. So I have e to the minus bt over 2m times a e to the I omega prime t plus b e to the minus I omega prime t. And this is the general solution to the equation. Using the fact that e to the I omega prime t can be written as cosine of omega prime t plus I sine of omega prime t, and the fact that x is real, meaning I need to pick the complex numbers a and b such that the resulting thing is real, I can also rewrite this guy as e to the minus bt over 2m times, let's call it maybe c cosine of omega prime t plus d sine of omega prime t. And now you may notice that's exactly what's written in the solution in the notes. A damped harmonic oscillator, cosine omega prime t plus phi, it's equivalent to the omega prime plus cosine plus sine, times an overall exponential. And this exponential is the curve that tells me how it damps out. So that's the solution to the damped harmonic oscillator. And the nice thing is, it gives me my damping, it gives my decay. There's one other kind of cool thing. So because we did solve this with complex exponentials, we can actually see the other limit pretty easily. So this was b squared small, less than 4mk. If instead I have strong damping, b squared greater than 4mk, then my solution for omega is actually a little different. So I still have IB over 2m, plus or minus, I mean I can write it out the same if you like, but now it's the square root of 4mk minus b squared over, is it 2m? 2m. And this guy right here is the square root of a negative number. So the square root of a negative number is simply I times the square root of the positive number, b squared minus 4mk. So now what you notice is that both of the modes, both of the omegas, are imaginary. And what that means is that the solution x is simply going to be e to the minus t times the first decay constant, kappa 1. And here, if I want to be careful, this decay constant is going to be what? B over 2m plus the square root of b squared minus 4mk over 2m. Kappa 2 is going to be the same thing with a minus sign. In other words, instead of having decaying oscillations, I simply have exponentials. I add up two exponentials. So just a little bit of terminology, certainly beyond the scope of this class, but just for those who are interested, what we've drawn here, where b is less than, b squared is less than 4mk, that's what's called underdamped oscillations. for b squared greater than 4mk, I have what are called overdamped oscillations. And that's where it just looks like the sum of two exponentials. So it never oscillates. It's too strongly damped to ever oscillate. And eventually it returns to equilibrium. Then right in between is what's called critically damped. That's the fastest, the best damp you can do. There are no oscillations, but the solution's a little bit more complicated. At any rate, that is certainly beyond the scope of this course, so I'm not going to go into that. Now, the one other thing I wanted to quickly mention for those who are interested is the idea of damped driven oscillations. So far I've talked about the case where I simply take an oscillator, take my ball in the jar, I let it go, and eventually after some amount of time it decays to zero. In practice, of course, that's not really what I want to do. You know, a clock, you want that pendulum to keep moving forever so that I can keep time. So what I do is I simply drive it just a little bit in order to keep things going. So the idea here is that I take my original equations of motion and I simply add one additional force. I add a force that is periodic in time, and the simplest thing I can do there is simply a cosine drive. Force is equal to F max times cosine of omega d plus t. So the places where you might do this, if I have a child on a swing, every time they come back to me, I push them. I apply a force that is periodic in time. And as we're going to see, it's actually really, really powerful when you drive this guy. Given that we are a little bit in overtime here, I'm just going to quickly mention the solution. Well, maybe let's go over the solution first, and then we can go over the videos. So the solution has the following form. It's a cosine omega d plus phi. So first off, there's no longer exponential damping. Why is that? It's because I'm driving. So instead of having that energy continue to get lost, I'm continuing to apply power to my system. And so I do oscillate at the same frequency as I drive. A brief caveat is there's actually a phase difference between the drive and the solution for x. That's not so important. It turns out this is actually something I can do pretty straightforwardly using the calculus that we already have. So with these complex exponentials, what I can do is I can simply, instead of talking about a cosine drive, I can do something that seems somewhat artificial, but it's not so crazy because I can, for example, always take the real part of the solution at the end of the day. I can do a imaginary drive. So I would have this drive force, which is just some overall force amplitude. Let's call that F0. That's a real number. Times e to the I omega drive times t. Okay? So previously I had a cosine. The way I could get a cosine out of this is I would simply take the real part of the driving force at the end of the day. And in fact, I can just take the real part of everything at the end of the day, and then I'll get the right answer. So we're going to go ahead and do this really crazy thing, and it turns out to work out really well. That's going to give me my F0 cosine omega t. All right, so my equations of motion with this complex driving force are mass times acceleration is equal to negative k times x minus b times v plus the driving force, F0 e to the I omega drive t. And again, I'm just going to guess a solution. I'm going to guess that my solution now is of the form x is equal to a e to the I omega drive times t. So let's see what happens if I make this guess. I've already taken the derivative, so I don't need to do anything else. Mass times acceleration becomes negative m times acceleration, that's I omega d squared. So that's the negative, the I squared becomes negative 1 omega d squared from taking the derivative times a e to the I omega drive t is equal to negative k times x, so that's just negative k a e to the I omega drive t, minus b times the first derivative, that velocity, so that's minus b times I omega drive a e to the I omega drive t. and finally plus that force, F0 e to the I omega dt. So again, because I've chosen all of these to be the same exponential, they cancel out. And what I'm left with is an equation for my amplitude. Let's bring all of these terms over to the right-hand side of the equation. My amplitude is A times negative m omega d squared plus ib omega z drive minus plus k times a when I bring it over to the other side. So I factored out the a, so plus k is equal to my drive force F0. In other words, the amplitude of my oscillations is F0 divided by negative m omega d squared plus ib omega d plus k. It's a complex number because of my dissipation, but it turns out if I take the real part and do things carefully, I can solve for that amplitude. And the solution actually turns out to be this expression. Square root F0 divided by the square root of k minus m omega d squared plus b squared over omega d squared. You may notice that is just the amplitude of this complex number. So that denominator is just the amplitude of A is equal to the amplitude of this complex number, which is its real part squared plus its complex part squared, square root of that. So that turns out to be the amplitude of the damped driven harmonic oscillator. And there's a really cool thing that happens at weak damping when I'm near the resonance condition. In other words, when omega drive is equal to omega, I get a very, very strong amplitude. You can notice that what's happening there is this term right here in the denominator goes to 0 on resonance. If omega drive is equal to the square root of mk divided by m, then that term is going to go to 0. And so the only thing preventing me from going to a very, very large amplitude is this drive. In fact, if there were no damping, this would be infinity. I'd be dividing by 0. So as that damping gets weaker and weaker, I go to larger and larger amplitude of oscillations. And it turns out this phenomenon called resonance can have some pretty cool effects. So here's one. This is a child who's going to sing. And he's a good singer. So what he's going to do is he's going to try to adjust his pitch. He's going to try to adjust his pitch so that he exactly hits resonance with this wine glass. There's one frequency where that wine glass is exactly oscillating on resonance. Here we go.
Mom, look.
Good singers clear their throats, as everyone knows.
It will never. Mom, I broke it!
So don't try this at home, but if you hit a glass on resonance, you can actually break it pretty easily. So what's happening there is you're hitting it close to resonance. The damping is weak enough. Glass is a pretty strong oscillator that amplitude just keeps driving and driving and driving, and not a very, very large force can create a huge amplitude. Now, there are some less fortunate examples of this, one of which you may know of is the Tacoma Narrows Bridge. So this was this very famous bridge that was built a handful of years ago.
As you can see, this bridge was exceptionally long and narrow, over half a mile long, only 39 feet wide.
Everybody was very happy. I mean, it was a huge construction project. They had all this ticker tape parade coming through. And then something happened a couple days later. People were driving across it, and they found that they hit it at exactly
on November 7th,
the wrong
the bridge
spot.
suddenly went into a twisting motion.
And here,
the wind speed was a steady 42 miles per hour. This was enough to keep the bridge oscillating in one of its natural modes of vibration with a period of 5 seconds.
This is not Disneyland. This is an actual bridge that was built not considering resonance frequencies.
A professor of engineering went out to see.
And that, my friends, is why you should care about damp-driven harmonic oscillations. All right, so with that, I will leave you to it. Thank you for staying till the bitter end. I don't think I had anything else I wanted to say. That's all I wanted to talk about for oscillators. So all the big ones, simple harmonic oscillators all the way through through arbitrary potentials. That is exam eligible. All of these damped and driven harmonic oscillations, they're not exam eligible, but I think they're something that are pretty cool. And in fact, they'll come back up again in 23, 26 when we talk about AC circuits. So thank you for staying all the way to the end. I will see you guys in a few days when we will start to talk about waves. All right, thanks.